Look at the accessory market for modern smartphones, and you'll find a single dominant design philosophy: thinner is better. Manufacturers shave cases down to a fraction of a millimeter to wrap the internal hardware without adding physical bulk. This ultra-thin approach perfectly accommodates the phone's internal circuitry, but it completely ignores the single most disruptive variable in the entire communication system: the water-dense tissue of the human hand holding it. This creates an interesting paradox in radio frequency engineering. Adding significant, deliberate physical bulk to a device's housing can actually increase its antenna efficiency. This added bulk doesn't act as extra armor against drops. Instead, it functions as a behavioral control mechanism, physically dictating exactly where the user is allowed to place their hands. The most advanced electrical engineering in the world fails the moment a device's physical shape invites a user to wrap their palm directly over the signal path. U.S. Patent 9698847B2 presents a structural blueprint that resolves this exact tension between human ergonomic habits and electromagnetic constraints. This patent diagram illustrates the baseline problem. A user naturally cups the bottom of the device for support. Contrast that with the patented solution in Figure 3b. The hand is physically forced toward the center, leaving the bottom completely exposed. The mechanism driving this shift in grip isn't a warning label or an instruction manual. It relies on specific physical protrusions molded directly into the outer edges of the case. This design treats the housing as a functional component of the antenna system, physically overriding user habits to preserve the integrity of the transmission signal. To understand why this is necessary, we have to look at the architectural layout of a modern smartphone. This schematic shows the primary transmission zones, the main cellular antenna area at the bottom, and the Bluetooth and Wi-Fi antennas situated at the top. Because the primary microphone is located at the bottom of the phone, human ergonomics naturally dictate that a user will cup that exact lower area during a call, placing their palm flush against the cellular antenna. Human tissue has a high water content. When you place that tissue near an electromagnetic field, it acts as a dielectric material, an insulator that can become polarized by an applied electric field. This proximity causes a phenomenon known in electrical engineering as detuning. The nearby human tissue absorbs radio frequency radiation, which actively shifts the antenna's resonant frequency out of its optimal band. When the signal efficiency drops due to this detuning, the device compensates. The internal hardware automatically increases the antenna's power output to push the signal through the interference. Driving that extra power drains the battery at a highly accelerated rate and simultaneously increases the localized radiation exposure to the user's hand and head. Standard industrial design has inadvertently placed the human body directly in conflict with the device's core communication function. The inventors of the patent conducted a controlled network analyzer experiment to quantify the exact mathematical penalty of this hand placement. Here is their baseline test setup. In position 1, the hand is intentionally held clear of the primary antenna area at the bottom of the device. Looking at the data for this uninhibited setup, we see the antenna hits its target center frequency of 850 MHz, a standard cellular band. The efficiency metrics are solid. The return loss, which measures the signal power loss due to reflection at the antenna feed point, is negative 15.63 decibels, equating to a minimal 2.78% total power loss. Now, look at the compromised test setup. In position 2, the user's hand covers the antenna exactly as it would in a typical phone call. The physical presence of the hand drags the resonant frequency completely out of the optimal band, landing at 721.81 MHz. This shift degrades the return loss and pushes the total power loss up to 3.09%. This line chart visualizes the severity of that shift. We see the sharp, efficient peak at 850 MHz, flattening and shifting downward to roughly 721 MHz when the hand is introduced. In a real-world scenario, that shift translates directly to slower data speeds, dropped calls, and a noticeably warmer phone. This empirical data invalidates the prevailing assumption of standard case design. Shaving a millimeter off a plastic casing means nothing if it allows a thick human hand to block the radio waves. Actively managing where the user places their hand is mathematically far more critical to device performance than minimizing the thickness of the housing. To solve the detuning problem, the engineers developed a highly specific structural solution called the group guide. This technical schematic shows the core of the design.
Instead of a uniform profile, the housing features exaggerated, bulky protrusions on the corners adjacent to the antennas. These dimensions are exact. To physically block a hand, the height of the protrusions, labeled here as H, must extend at least 15 millimeters outward from the device body. There is also a strict width constraint. To break the user's ergonomic habit, the protrusions, labeled W, must occupy at least 1/4 of the total width of the housing frame, labeled F. The physiological reasoning is straightforward. These exact dimensions make it physically uncomfortable and virtually impossible for an average human hand to securely wrap around the top and bottom transmission ends. This discomfort intentionally forces the user to seek a better grip, sliding their hand into the designated recessed gripping region, right in the center of the device. But geometry is only half the equation. The final engineering constraint is material science. Adding bulk to block a hand is entirely useless if the bulk itself is conductive and interferes with the signal. To prevent this, these massive protrusions must be manufactured from materials with a low dielectric constant and a low loss tangent. That means utilizing specialized non-metallic foams, rubbers, or highly specific plastics that radio waves can pass right through. The grip guide is a highly precise mechanism combining rigid geometry to repel the human hand and specialized materials to remain entirely invisible to the radio frequency waves. So we return to our initial paradox. Bulky cases can be superior to thin cases, but only when that bulk acts as a calculated ergonomic barrier protecting the transmission zones. Look at the optimized system in action. Top and bottom antenna zones are open to transmit, while the hand rests securely in the central gap. Here, the radiation propagates cleanly into free space, rather than fighting through the water density of a cupped palm. This clean transmission creates cascading benefits. Because the signal isn't blocked, the internal circuitry doesn't have to constantly boost power output, which preserves critical battery life. And by keeping the primary signal path away from the skin, localized radiation absorption for the user drops drastically. This type of behavioral override is vital far beyond consumer smartphones. It applies directly to tablets, to enterprise hardware, and even wireless medical devices, where signal integrity can be a matter of absolute safety. It reinforces a core engineering lesson. The most highly optimized internal hardware cannot survive a poor external affordance. The elegance of the grip guide is that it doesn't rely on warning labels or begging users to hold their phones correctly. It forces compliance entirely through physical design. True innovation in consumer electronics happens when designers acknowledge and respect the unforgiving intersection of human behavior and electromagnetic physics.